All right, ladies and gents, what we're going to attempt to do here is use a differential equation to work backwards to find a general or particular solution. In general, we're going to see if we can give you everything you need to know regarding differential equations and how to work back to a quote-unquote original equation here. To do this, we're going to use a process called separation of variables. So here we're given dy dx, and it says first find a general solution for the differential equation. So that just means that we're going to separate variables and work back to what would be the original equation via anti-differentiation. So you can see my dy dx equals x squared over y. I'm going to multiply both sides by y. So I get y times dy equals x squared, and multiply both sides by dx. And I'm going to take the antiderivative of both sides. On the left, I have 1/2 y squared, and on the right, I have 1/3 y cubed plus c. Now you might ask, why don't I have a plus c on the left-hand side too? Well, the bottom line is I can have a plus c on the left or the right or both, but since two constants add together to be another unknown constant, the convention is to just put it on the independent variable side, and that's going to come into play and help us out later. So it's not solved for y, but what I have right here is my general solution. It's a solution to my differential equation. It is the antiderivative of what I started with, and it's the general solution because it works for any c value. Now, this particular question asked me to find the particular solution through the point 3, 2. So to do that, I'm going to plug this point in right away before I do anything else. So I'm going to take 2 and put it in for y, so 1/2 2 times 2 squared equals 1/3 times 3 cubed plus c. And now I'm going to solve for c. On the left-hand side, I get 2 equals 1/3 of 3 cubed, which would be 9, plus c, so c equals -7. So what that means is, and let's get a little bit of room down here, what that means is my c is equal to 7, so 1/2 y squared equals 1/3 x cubed minus 7 is my particular solution through the point 3, 2. Now, many times on your AP test, they're going to ask you to do this and put it in y equals form. So let's go ahead and go down here and get this in y equals form. To do that, I'm going to start with my particular solution. I'm going to multiply everything by 2. So I get y squared equals 2/3 x cubed minus 14. And I have to take the square root of both sides, so y equals plus or minus the square root of 2/3 x cubed minus 14. Now, if I kind of zoom out, remember my original point was 3, 2. That means that my final particular solution is going to be y equals the positive version of the square root, 2/3 x cubed minus 14. And you might say, well, that sounds kind of dumb. Why do I have to include this plus or minus here with the square root? Well, think about if we were to change this problem just slightly. Think about if we were to have a particular solution through the point 3, -2. If I were to change my work along the way, the only thing that would change here is that this would be a -2 when I input my y value. It wouldn't change any of the work along the way. In fact, it wouldn't change anything else down here except when I put 3 in for x in my particular solution, I'm expected to get out a negative value. I'm expected now to get out a -2. So at the end of the day, you need to come up with a particular solution that works for the point that you're given. You're going to have to go back and make sure that if you indeed do plug 3 in, that you get out 2 or -2. If not, something happened along the way. You did something wrong with your anti-differentiation, or you made some algebra mistake. Just be careful and be mindful of these special cases like this when you have to take care of the plus or minus square root. So how else can we extend this idea of differential equations, and what else can we use this for? Well, even though these variables can be separated and integrated, not every single case, not every single differential equation can be. We're going to flip to another slide, and we're going to look at what's called a slope field for this same differential equation. Now, even though I can find the antiderivative of both sides here, I can separate variables for this particular differential equation. Like I said, not everyone can. So we want to have a method to look at what the original equation or the original graph might look like in the event that we can't separate variables and solve. So we're going to create what's called a slope field. And a slope field uses this differential equation to get an idea of what is actually happening, get a picture of our graph, get a picture of what the original function might look like. And it's going to use little tiny slope lines to do it. Here's how it works. Let's take the point 1, 1, for instance. I'm going to evaluate dy dx, evaluated at the point 1, 1. And in doing so, I'll put 1 in for x, 1 squared over 1, which gives me a result of 1. That means at the point 1, 1, I'm going to have a nice little positively sloped tangent line with a slope of 1. And you can kind of see it there. And I would continue that. I could go in here and I could change my point. I could say, what happens at the point 1, 2? Well, I put 1 in for x, I put 2 in for y, and I get, don't like that. Oh. We'll get there. I get 2 in for y, and I get a value of 1/2. So I should now have a slope that's slightly less steep at 1/2 at the point 1, 2. At the point 2, 2, I can sort of slide down here and say, okay, dy dx, evaluated at the point 2, 2. I end up with 2 squared over 2, which is the same thing as 4 over 2, aka 2. So at the point 2, 2, I have a little steeper slope with a slope of 2. And I would continue to fill out at every single one of these points along the way. Every single one of these guys would get a little mini tangent line slope. This will essentially give me a picture using these slopes of what my original function looks like. Before I show you the full slope field, it's important to note, if you ever have a 0 in the denominator, if you ever have an undefined differential, like in this case, it would be anytime y equals 0, anytime along that x-axis, we're just going to leave those points blank. Normally, we would fill along the axis. For instance, at the point, 0, 2, I'd have a slope. There would really be like a red point here, or should be, and I'd have a slope of 0 here. I'd actually also have a slope of 0 at 0, 1. But anytime your differential equation is undefined, we're just going to leave those points completely blank. Let's take a look at what the slope field looks like for x squared over y. And here it is. And I can zoom in if I want to get an easier picture. And I have what this might look like. And I can sort of see how a curve might run through this particular slope field. If I zoom out, it kind of reminds me of like a magic eye, or if I sort of make things blurry, I can see what this curve might look like as it sort of maybe comes in down along this way and curves back through here and sort of does one of these things, right? Something to that effect. So what happens if I take my particular solution from before? Remember my particular solution that was, and I did not solve this for y when I put it in, but it was right here. Let's see if we can circle it. There we go, right there. And I take that particular solution and I put it into my slope field. Let's see what this thing actually looks like. There you go, you can see it in green. There it's gone, now it's back again. So that curve actually fits into my slope field. Let's try some different values here. What if I tried this through the point, I believe I used 0, 2, and using the point 0, 2 found the particular solution right here. If I turn that on, I get that curve. Notice it literally goes through the point 0, 2. I continue just by changing that c value to get something at +4 and then +6. And you can see how these curves continue to change but still stay along the slope field. What these things all do is they're really giving you an idea of what the original functions look like, given this derivative, given that differential equation, given that dy dx. These are all different particular solutions that go through different points along the way. That's what a slope field does. It gives you an idea of what the original graph might look like, whether you can take the antiderivative of something and whether you can separate variables or not. So we went through and we found a general solution and a particular solution through a couple different points. We created a slope field, and there was our big slope field. Let's see if we can try another example real quick where we have to separate variables. So here's dy dx, and it's equal to x cubed y, and we're going to go through the point -2, 1. So I'm going to separate variables. I'm always going to put my y's on the left and my x's on the right. And the reason I'm going to do that is I always want to have my dy and my dx has got to be in the numerator. They need to come up to the top of these fractions. They need to be at a point where I can take the antiderivative of both sides. Of the last one, I take the antiderivative with respect to y. I get the natural log of the absolute value of y equals, on the right-hand side, 1/4 x to the 4th. And remember, I'm going to put a plus c in on the independent variable side. So there's my general solution. Before I solve this for y or do anything else, I'm going to go through and put in my x and my y right away. That's actually a point where you can get a spot where you can get some points on your AP test just by plugging in your initial condition. So I have the natural log of the absolute value of 1 equals 1/4 times -2 to the 4th plus c. If I simplify this guy, I get 0. Natural log of 1 is 0 equals 1/4 of 16, so 4 plus c, so c equals -4. That means that I have that the natural log of the absolute value of y equals 1/4 x to the 4th minus 4. Now, what if I was asked to solve this particular solution for y? If I need this final answer in the form y equals, well, I got to break y free out of this natural log. So I'm going to exponentiate both sides. And be careful. When you exponentiate both sides, you're raising both sides and making both sides a power of e. But what doesn't happen here is absolute value doesn't magically disappear. You end up with the absolute value of y equals e to the 1/4 x to the 4th minus 4. And technically speaking, this is all in the exponent here. Now, this value is always positive. On the right-hand side, this is always a positive value. E always spits out a positive output. But the problem is, if you remember, I need this to go through the point -2, 1. So if I put a negative value in here, do I get out 1? Let's take a look. Y equals e to the 1/4 x to the 4th minus 4. Remember, that's all in the exponent. So if I just drop off this absolute value, how does this thing behave? Well, I can check myself. I can put -2 in for x, right? X equals -2. And I would end up with e to the 0, which is equal to 1. How can we change this problem to make this a little bit more challenging? Well, what if I took this and went back and made this point -2, -1 instead? Let's change colors here. We'll put a little box in there. If I change this guy, just like I did before, now all of a sudden, you'll notice I'll zoom out here a little bit instead of flying around. The only part of my work that changes here is I put a negative in for 1. The natural log of the absolute value of -1 is still 0. My work all the way down through this step stays the same. The problem is now, at the end of the day, I need to get out a -1. So my final answer for this case is going to have to be y equals -e to the 1/4 x to the 4th minus 4. I'm going to have to deal with that absolute value. And when I drop that absolute value off, I'm going to have to address whether I want the right side of my equation to be positive or negative. So here again, the initial condition, that initial point, is going to dictate how my function ends up. I have one more example for you, right? And this is an exponential growth sort of example. This is a problem where dy dt equals ky. So all I've done is I've changed x to time, to t, and now I have a function where, if you think about what this means, the growth rate, right, the rate of growth of, the rate of growth of this function, dy dt, that's the growth rate of y, is based on some proportional constant, k, some number that I don't know right now, times the amount of whatever it is that exists. This is different than normal. Normally, the growth rate is based on time. As time progresses, the rate of growth either goes up or goes down. But now, dy dt is based on the amount that we actually have. This is important for bacteria growth or decay or radioactive decay, because the growth rate is based, again, on the amount of stuff present. Think about a population of animals. The more animals there are, the faster the rate of growth of that population. This is true for these types of functions. So let's see what kind of original curve this results in. I'm going to switch back here. We'll go to blue. And let's separate variables and go to work. I have dy over y equals k dt. And it's important that I'm going to leave any constant, whether it's a k or a 2 or a 3 or a pi or a 1700. I'm going to leave those over on this independent variable side. I'm going to leave those guys over with my x's and my t's to make my solving down the road a little bit easier. I'm going to take the antiderivative of both sides. On the right, I get the natural log of the absolute value of y equals k times t, the antiderivative of the constant, times t with respect to t, plus c. Now, if I solve this thing for y, if I exponentiate both sides, I end up with y, assuming the positive output here, equals e to the kt plus c. And again, this is all in parentheses here in my exponent. Now, you may not usually see it written this way, but this is actually an exponential growth problem. If we use a little bit of our algebra skill, our exponent rule skills, we can rewrite this as y equals e to the kt times e to the c. All I did was break down that exponent. I added exponents, which means I can multiply like bases. So all I've done is use my exponent rules to break this thing down algebraically. But I think I can rewrite this e to the c, because e is just a number and that constant c is just a number. So I'm actually going to give this a new name. And I'm going to make this y equals capital C times e to the kt. And this you may see in an exponential growth problem, right? Where you have a graph that maybe looks something like this, where you're really getting on your horse and accelerating rapidly, or even a population that's growing exponentially, or perhaps decaying exponentially. And again, this is based on the fact that dy dt equals ky, that the growth rate is based on the amount of y, the amount of the population that exists. That leads us to our exponential growth. So going back, where does that come from? This is all enabled. This whole scene is enabled by the fact that we can separate variables to find general and particular solutions. We can do that. We can look at them as in slope fields, right? And we can do that for all sorts of different examples, making sure that our final point, whatever the case may be, works, right? That our final equation always results back and makes our initial condition true. And then finally, we can extend this out to exponential growth and decay problems. And this sort of exponential growth relationship, this proportional growth relationship, results in an exponential growth function. And then you can use that to sort of unlock some different problems, as you'll see in your practice. Good luck with your differential equations. Take care.